So today, Matt Dodelson from CERN will give the particle theory seminar. This is on extremely recent work. He has agreed to give this talk on very short notice. I think I asked him a week and a half ago. So thanks a lot, Matt, for agreeing. And he will tell us about gravitational orbits and quantum scars. Take it away, Matt.
Okay, well, thanks so much, Luca, for the invitation. I'm hearing some noise.
Yeah, sorry.
Okay. Okay, well, thanks, Luca, for the invitation, and I'm very happy to be here virtually today. I'll be telling you about this paper that I put out a few weeks ago with Sasha Zhiboedov here at CERN. So here's the outline of the talk. I'll first motivate these results by reviewing a recent development in condensed matter physics known as many-body quantum scars. So these are non-thermal eigenstates in the spectrum that are very interesting to discuss. And the analog in our case will be gravitational orbits in anti-de Sitter space around a black hole. So I'll first review the properties of these orbits and then compute their decay time. So in the next part, I'll connect these orbits to the light cone bootstrap, and in particular, use them to obtain new predictions for dimensions of heavy light double twist operators. And finally, I'll close the story by connecting these orbits to quantum scars in a certain perturbative limit. And I'll conclude with the outlook. So that's the outline. So let's start with the motivation. So consider a non-equilibrium state psi in a chaotic theory. So the statement of chaos is that after a sufficiently long time, if we compute expectation values in this state, they should approach their values in a certain thermal ensemble with a certain temperature. In other words, they should thermalize. Now we can ask, is this true in all theories, in all states? And the answer was found experimentally to be no. So an experiment was done in 5 years ago. An experiment was done involving Rydberg atoms, which are a certain type of two-level system. You can think about them in that way. And an observable in this chain of atoms found revivals instead of thermalization of a certain observable known as the domain wall density. So I won't go into the details, but the point is that this does not thermalize, it oscillates, it revives over time. So in this case, the initial state is a very highly tuned configuration. It has Z2 periodicity along the chain of atoms. And the reason for these revivals, it turns out, is that this state has a very large overlap with atypical non-thermal energy eigenstates. And that leads to the revivals. So let's try to understand these non-thermal eigenstates by looking at a much simpler model, just a free particle that's bouncing off the walls of a billiard. So this is called the stadium billiard. It's shaped like a stadium, and we consider a particle bouncing around, and it just reflects off the walls. So most orbits in this system are chaotic, and they explore all the phase space, but they're very special orbits that just bounce up and down against the top and the bottom walls. So now let's quantize the system. So these plots are from this paper. And we quantize the system by solving the Schrodinger equation with Dirichlet boundary conditions at the boundary of the stadium. And so this is what an eigenstate looks like for a chaotic orbit. So on the left-hand side is the classical orbit. On the right-hand side, it looks like a random superposition of plane waves. So that's a chaotic state. However, as I said before, there are also periodic bouncing orbits that just bounce up and down, and an orbit that starts out close to that periodic orbit is going to stay almost periodic for a long time. In the quantum theory, the statement is that there are non-chaotic eigenstates that don't look like a random superposition of plane waves. They look like they're supported mainly in the center. So that's the right-hand side. So these are very atypical eigenstates, and they're called quantum scars. Now, in the Rydberg atom experiment, the analog of the Z2 state that's prepared at the beginning is a wave packet in the billiard system that's focused very close to the periodic orbit. This wave packet has a high overlap with the scars, and so it shows the revival. So after this experiment was conducted, the next step was obviously to theoretically find these scars in more complicated many-body systems than the billiards model. And there's a vast literature, and many examples have been found. Here are some of them. So these scarred eigenstates violate ETH and have a sub-volume law entanglement entropy in these states. So that's in contrast to a thermal type state, which has a volume law scaling of the entanglement. Since they're atypical, they occupy a very small subspace of the Hilbert space. And another feature that happens some of the time is that they come in a tower of evenly spaced states. In that case, there's usually a spectrum generating algebra, which generates that tower of states. So what I want to do in this talk is to identify states that look like scars in a certain limit in holographic systems. And the analog of the scars will be orbits around an ADS black hole. And I'll show that they share many properties with scars in a certain limit, which I'll describe in detail. So are there any questions about the motivation?
So maybe just the expectation is still that most systems don't have scars, or like if I kind of start, maybe in the lattice community, if I start with some random spin chain, it seems rather hard to build systems. I mean, you need some effort to build some of these systems with scars, right? The more generic situations that you don't have some.
Yes, absolutely. Yeah, I'm not trying to quantify it, but practically it's harder to find systems with scars than without them. Yeah.
But I get, okay, but then a question would be, so you're going to show us that in holographic systems you do have scars, but is your expectation that in a generic CFT that's not holographic, you would have scars?
In a generic CFT, which is not holographic, yeah. So in that case, we would not have scars because we'll see that the lifetime scales with G Newton, and if G Newton is 1, then these things are not going to be long lived. Yeah. Okay, so let's now review orbits in ADS. So consider a light particle. It has mass m sub L. L stands for light, and it's orbiting around an ADS full black hole. I take 4 dimensions just to be specific. In less than 4 dimensions, there are no stable orbits, so the problem is not interesting. So also, I'll take the mass to be much bigger than 1 in ADS units. In this case, the wave function of the particle is highly localized near the orbit, so we have a semi-classical picture of this orbit state. So here's the metric. The redshift factor has the ADS form at large distance, and it's perturbed by this mass term. Mu is like the mass. Here's the equations of motion for a time like geodesic. We have 2 conserved quantities, the energy and the angular momentum, and eliminating those in the geodesic equation gives an expression for R dot. And this expression looks like a particle just moving in a potential. the potential is given by this form. So here's a plot of the potential for large enough L, for large enough angular momentum. And in this case, the potential develops a stable minimum. The orbit is going to sit at that stable minimum. So in the case of the circular orbit, we just have to minimize the potential, and we can parameterize E and L as a function of the radius of the orbit. And here's this form of that. So a key point is that in the denominator here, this has to be greater than 0, and so these orbits only exist outside of the photon sphere, which is given by this quantity. So since I'm only interested in stable orbits, I'll consider the case where V double prime is greater than 0. So that's an additional condition. So now we have an innermost stable circular orbit, and this is going to depend on the mass of the black hole. For small black holes, it's at r equals 3 mu, which is a familiar equation. And for large black holes, it's at r equals 15 mu over 8. So we can solve these equations for E as a function of L, and we find this formula. So note that this is an expansion in mu over square root of L. So what that means is that at large angular momentum, we don't see the black hole anymore. In this limit, the energy is just equal to L plus 1, and that's the energy of a circular orbit in ADS. So in other words, the small mu expansion or the large L expansion is equivalent to expanding around pure ADS. So what's the boundary dual of these orbits? So for large mass, the scaling dimension is equal to the mass, and the spin is the mass times the angular momentum. So that means that we have a Regge trajectory, which is a family of operators parameterized by spin, whose dimensions are analytic in the spin, and it's given by this form. So here I just add the dimension of the black hole, which I call delta H, to the dimension of the orbit, and that's given by this. And we can write this in the following form. So the first three terms in this on the right hand side are the ADS formula for the dimension of the orbit, and then the last term is the corrections due to the black hole. So here J has to be bigger than some minimum spin, because otherwise the potential does not have a minimum for small spin. So the anomalous dimension is defined like this, and because the corrections to E of L are small at small mu or large J, this anomalous dimension vanishes at large spin. So here's a plot of the Regge trajectories as a function of spin, and so the red line is the order mu answer, the black line is order mu cubed, and then the blue line is the exact answer. And you see that it converges very quickly to the exact answer. So that was the circular case, but there are also stable non-circular orbits, and these oscillate around the minimum of the potential. So in the case of a general orbit, there are three turning points: RB and RA and RC. RA and RB are inside the potential barrier, or sorry, they're confined to the potential barrier, and RC is between the horizon and the potential barrier. So again, we can solve for E and L as a function of RA and RB. Here, Y is RB over RA. So these the spectrum of allowed y's or eccentricities of the orbits is quantized according to the Bohr-Sommerfeld condition, because we have a particle in this potential. And I'll go into this in a lot more detail later. So here I'm writing the Bohr-Sommerfeld condition, first written down by Festuccio and Louvre. And this is the leading order in delta L. So this is for very large masses where the particle becomes effectively classical, effectively localized on the orbit, on the classical orbit. So note that the particle can't oscillate too much because it'll just fall into the black hole. And so n is bounded above by n max for stable orbits. So again, we can write the Regge trajectory delta HL, and now it's a function of n, the oscillation number, and j, the spin. So it takes the ADS form plus a small anomalous dimension gamma, and it applies for n, it applies for n less than n max and j greater than j min, that should say.
Sorry, these n max and j max, they're order 1, or in terms of the boundary CFT, what do they depend on?
They depend on the mass of the black hole. There's a certain scaling which you can work out, but yeah, it depends on how big the black hole is.
So you would say in terms of delta H. Let's see.
But sorry, this should be J min. So J should be greater than J min. I mean, for instance, for large black holes, J min is in D equals 3, which is a 4-dimensional ADS. It's J min equals mu squared. Yeah. Okay. So there are many simple generalizations of this orbit calculation. One can consider higher dimensions, charged black holes, spinning black holes, et cetera, et cetera. Here are two interesting cases that I'll briefly touch on. So, so one example is we could have higher derivative terms in the Lagrangian, and then the black hole background is going to receive small corrections, and we can compute the effects of these corrections on the Regge trajectories. So, for instance, with the Gauss-Bonnet term, the redshift factor is modified to this form. Alpha is the Gauss-Bonnet coupling, and this leads to small corrections for small alpha in the anomalous dimensions of the Regge trajectory. So here we are right here. So another example would be black holes in de Sitter space. For these black holes, the mass is bounded from above by the Nari bound, which is just a number. And the kind of peculiar thing is that the spin of the orbits in this case is not just bounded from below, it's also bounded from above. So for instance, this is for small black holes, and it takes this form. Okay, any questions on the orbits? Okay, so let's move on to their decay. So the bulk emits classically stable orbits, but in the full theory, we want to understand their eventual decay. So let's think, what are the possible decay processes? Well, one process is that the potential barrier is not infinite, it's finite. And so the particle can tunnel into the black hole. So that's allowed. And the other process is gravitational radiation. So the orbit can emit gravitational radiation and lose energy to the gravitational field. So that's something that has been computed in asymptotically flat space a long time ago, and we can try to compute in ADS also. So just parametrically, the gravitational radiation is suppressed by 1 over CT or by G Newton. And we will find that the tunneling rate is non-perturbatively suppressed in spin, at large spin. So perturbatively in spin and at infinite CT, these orbits are stable objects. In the full theory, they eventually decay. So instead of considering the gravitational radiation, I'll consider a simpler problem. And in this model, I'll take a massless scalar field phi, and I'll couple it to the orbit by this coupling term. So phi here is linearly coupled to the world line of the orbit, and it just propagates freely up otherwise. To obtain a rough estimate for the gravitational radiation, we can replace kappa by delta L times square G Newton. So that gives the right scaling with G Newton and delta L. So there's one key difference between the asymptotically flat space and the ADS case, namely for asymptotically flat black holes, the radiation can either escape to infinity or it can fall into the black hole. In fact, most of the radiation escapes to infinity, and only a small amount makes it into the black hole, at least for orbits that are very far away. In ADS, on the other hand, the radiation that would have escaped to infinity just bounces off the boundary and it falls into the horizon. So the only energy flux that we need to compute is the flux through the horizon. So here's the expression for that. So this is the power emitted through the horizon. D here is the torus coordinate, and we should evaluate this expression on a solution to the wave equation for phi that's purely ingoing at the horizon, and it falls off at the ADS boundary. So let's write down that wave equation. Here it is. So on the right hand side, we have the source of this wave equation in Fourier space, and on the left hand side we have the source, and the potential takes this form. So Cardoso and Lemos showed how to compute the solution using a Wronskian analysis. And what they found was that it's equal to this expression. So here, YJM are the spherical harmonics. R naught is the orbital radius, and these CJMs are the things we need to compute. So these coefficients CJM are defined as follows. We need to solve a solution to the wave. We need to solve the wave equation without a source, and we need to find a solution that falls off at the ADS boundary. So in other words, it should go to 0 as z goes to 0, and it should and that's it. And it should solve the wave equation. And then we can read off Cj omega by the coefficient of e to the I omega z near the horizon. So let's work with large black holes. In this case, it's nice because we can actually use a WKB approximation to solve for these Cj omegas. So in this paper by Cardoso and Lemos, they solved the equation numerically, and we want to see how to do this analytically. So at large J, the radiation potential takes this form, and we see that it looks like a good WKB limit. So here's the WKB solution, where this S is defined as follows. Now there's a technicality here, which is near the boundary, near the ADS boundary, the WKB approximation fails. But in that limit, we can solve the wave equation exactly, and matching the two gives the proper normalization of the wave function. So now we we have the WKB wave function, and we just need to compute these CJMs. So it turns out that the dominant regime is where the spherical harmonic mode number M is very close to J, and J is much greater than 1, and also J is less than mu squared. So in that limit, we find this formula for CJMs, and then we do the sum over M, and we find this formula. So this is for J much greater than 1 and is less than mu squared. So in this plot down here, I plot the power as a function of J, and we see this initial growth of the power in J, and that's what this formula captures. For J much greater than mu squared, we get exponential suppression, and so the sum is cut off at J equals mu squared, and we finally find the total power, which is equal to this. So now we have the power, and we can compute the decay time, which is the thing that we want. Another difference from flat space radiation, in this case, the power spectrum is dominated by both large J and M close to J. So what that means in position space is it's synchrotron, meaning it's highly focused around the equatorial plane. In the asymptotically flat case, it's completely different. The radiation is dominated by M equals 1 or M equals 0. M equals 1, the fundamental frequency of the orbit. So it's a very different type of radiation in ADS. Okay, so that's the power, and now we can determine the decay time. So we assume that the energy of the orbit is much less than the black hole mass. So in this case, the final state is a black hole, and it's spinning very slowly, and it has approximately the same mass as the original black hole. And so let's consider an adiabatic process. So the energy of the orbit is delta L times R naught of t squared. R naught is the radius as a function of time. And now we know the power, so we just compare the derivative of this with the emitted power. And that gives the following radiation time. So at very small kappa, it goes to infinity. In that case, the coupling of the orbit to the radiation field is very small, so that makes sense. Also, for an orbit that's very far away, it will go to infinity like a power of R naught because it takes a longer time to fall in. Note that in the analogous gravitational problem, the radiation time scales with CT. So at infinite CT, at 0 G Newton, this thing is stable to radiation. Okay, so that's the radiation. And now we need the tunneling. So I'll recall that we had this potential, and we had a finite potential barrier, and it can tunnel over that barrier. And the turning point on the other side of the barrier, we called ZC. So then the decay rate for tunneling is equal to this exponential factor, which is an integral from the turning point over the barrier to the next turning point. So this is exponentially expressed in delta L because the action is proportional to m for a point particle. So in other words, for very large delta L, this is very well localized on the orbit, and we expect this thing to be almost stable. So let's evaluate this integral. For a circular orbit that's very far away, it turns out, so we know that E is approximately L, because that's the ADS answer. And here are the other two turning points. And one finds this answer. So gamma is exponentially suppressed in spin. For large black holes, the exponential suppression is e to the minus j over mu squared. And for small black holes, it's mu to the 2j. So this is exponentially small at large spin. It's non-perturbatively small. So that's the decay rate. And now the decay time due to tunneling is the inverse of that. And what you find is that the condition for tunneling to dominate over radiation can be written like this. So let's set kappa equals 1 over square root CT, which is appropriate for gravitational radiation. And what we find is that for large enough spin, gravitational radiation starts to dominate over tunneling. The reason for that is essentially that tunneling is exponentially small in spin, and radiation is only polynomially small in spin. Okay, so I think that should cover the decay time of these orbits. Are there any questions about that calculation? Okay, so now let's go to the bootstrap. So the light cone bootstrap is a very powerful tool for analyzing any CFT at large spin. So in particular, in the case of two light operators, any CFT in more than 3 dimensions contains double twist operators, which are formed out of these two operators. So we call those OL, OL, n comma j. N and j are two parameters that parameterize this family of operators, and the dimensions of these operators are almost the dimensions of the operators in ADS, just as before, up to some anomalous dimension. And the statement of cluster decomposition that we can separate operators at large spin is that at large spin, this anomalous dimension goes to 0. So this double twist operator, OL, OL, corresponds to a binary system of light operators in ADS, and they're just orbiting around each other. So n here is going to parameterize the eccentricity of the orbit, and j parameterizes the spin of the orbit. So now it's interesting to ask, instead of these operators being light, let's take one of them to be heavy. So we take one of them to be a black hole. So now naively, what you might expect is that we have operators which are double twist operators formed out of O heavy and O light. And these would correspond to an orbit around the black hole in ADS. So that can't be true, because I just showed that these orbits are unstable to radiation and tunneling. So these operators cannot be energy eigenstates. However, a useful picture is to consider the infinite CT limit and only work perturbatively in one over spin. In this limit, these operators are energy eigenstates. Away from this limit, they become resonances with a very long decay time. So another way to say this is, if we work at infinite CT, then the only decay effect is tunneling, and we saw that that was non-perturbative in spin. So in order to probe the horizon of the black hole in the boundary CFT, we need to look at non-perturbative in spin effects in these operators. So now the heavy light Bootstrap program has the goal of computing these the operator dimensions and OPE coefficients of these double twist operators OH, OL. And they work perturbatively in spin and also perturbatively in black hole mass. And they therefore miss effects due to tunneling. So now let's describe the relation between these double twist operators and the orbit states that I've discussed previously. So let's first recall the concept of a quasi-normal mode. So for a black hole, we can't talk about normal modes because a wave can just fall into the horizon. And so instead we have quasi-normal modes which have complex energies and are purely ingoing at the horizon. So these are resonances, just like these operators O heavy, O light should be. And so we might expect that they're somehow related, and indeed that will be the case. So the quasi-normal modes, we should think of them as quantized wave functions for the classical orbits that I described earlier. For large spin, they take the following form. So they have a real part, which is large or 1. Actually, it's large. And then they have an imaginary part, which is exactly equal to this tunneling rate. So this is the thing that's non-perturbatively small in spin. So if we only work perturbatively in spin, it's natural to propose that these operator dimensions of the double twist operators, the heavy light double twists, is equal to delta heavy plus the quasi-normal mode energies, because the imaginary part is non-perturbative. So it's possible to derive this relation, and you can do that using the fact that quasi-normal modes are poles of the Whiteman function, and along with the ETH ansatz for 3-point functions. So I can't get into the details of that, but you can see our paper to see how we did that. But the punchline is that if we work perturbatively in spin, the spectral density takes the following form. So we have a pair of quasi-normal modes here, and they're complex conjugates. And here the imaginary part of these guys is non-perturbative in spin. But this is a continuum of states because it's a resonance. However, if we work perturbatively, we get a delta function in the spectral density. So we get a delta function at exactly the dimensions of the double twist operators. So the way to think about it is that these double twist operators are not actually energy eigenstates, but it kind of emerges in the perturbative limit.
Sorry, but wouldn't you say that there exist exact energy eigenstates? It's just that the things that you're, the state that you're realizing geometrically has a large overlap with it, but isn't exactly that?
Yeah, so there certainly are energy eigenstates, but they are not double twist operators.
I guess it's a question of what you mean by double twist operators. Like there is an energy eigenstate that has almost the same quantum numbers as.
Yes, a black hole. A black hole. Yes. Yes. Yeah. Right. Yeah, I guess it does depend on what you mean by these operators, but I think the way to think about it is that let's just work at finite spin. Then the things that contribute mainly to the OPA limit of the heavy light 4-point function are these resonances. And then as we take j to infinity, they condense into exact eigenstates.
Sorry, I don't understand that statement. So if I compute a 4-point function in a black hole background, so 2 heavy operators and 2 light operators, and run the light cone bootstrap argument, doesn't that tell me that there are exact states in the spectrum without any complex contribution to their scaling dimension that are actual operators in the spectrum?
Yeah, but the problem is that computation only knows about perturbative and spin things.
Yes, but they're yeah, sure. You compute the scaling dimension, the anomalous dimension in a perturbative series in 1/j.
Yeah.
But there is no complex contribution.
Yeah, perturbatively and spin, I agree. They look like exact eigenstates.
Sorry, you're saying if I manage to resum that 1/spin all the way in perturbation theory, I'd get a complex contribution?
If you were able to do it non-perturbatively, yeah.
Nice. Okay.
Yeah. Okay, so now let's do some computations. Okay, so the fact that these dimensions of these operators are actually equal to the real parts of quasi-normal energies is actually very powerful for computations, because we can just compute the quasi-normal energies and we don't have to think about the bootstrap. So let's give a simple perturbative scheme for computing these quasi-normal energies. And I want to match with the bootstrap results, and I want to extend them as well. So previously, these things were computed in the bulk either by computing the phase shift or by doing just a direct perturbation theory in the bulk. But this is a more powerful tool that will give answers to all orders in the black hole mass. So the quasi-normal modes satisfy this wave equation. So here, nu is defined in this form, and nu is a more useful parameter than the mass, as we'll see in a second. And here's the potential. So now let's take the large nu limit, and we do that in a way by changing variables from j to k and scaling nu in the process, and we also scale omega. In this limit, we get exactly the potential that governs the classical geodesic motion. So this is exactly the same thing that we had before. And the reason that we took the limit in this way is because the corrections to this potential are order 1/nu squared, not 1/nu. So it's more convenient. So now to leading order in 1/nu, if we want to compute these quasi-normal energies, we have the Bohr-Sommerfeld quantization condition. So it takes this form. So this is what I wrote before, but it has an additional 1/2 that we know is there in Bohr-Sommerfeld. However, the bootstrap guys are very powerful, and they have some more complicated results. So we want to be able to match the full results, and so we need to go to high order in 1/nu. So it's possible to actually do this. So we make a WKB ansatz for the wave function. So now instead of just one WKB action S, we have an infinite series of them. And then using the wave equation, you can find that these guys satisfy a recursion relation, and it takes this form. So the 0th order one is the familiar answer. And then there's a higher order recursion relation. And here Q is equal to the potential minus U squared. So now what you need to do to compute the quantization is to match the wave functions at the turning point using area functions to all orders in 1 over nu. So that it's pretty complicated, but it was done a while ago, and the answer is very simple. So here's the form of this of the all orders quantization condition. So we will only need to second order in 1 over nu, and that gives the second term here. So this is this 1 over 96 guy. So here this is a contour integral around the two turning points, and this is an integral from the first turning point to the other. Okay, so now to evaluate this formula, we can do it easily in the case of a nearly circular orbit, which in terms of n means that n is fixed as nu goes to infinity. So now you have to plug in these q's, do perturbation theory about the minimum, and then solve for the energy u in a power series in nu. And you find this complicated looking expression. So it's in terms of derivatives of the potential, and it certainly depends on n, which is the oscillation number. And the really powerful thing about this formula is that it applies to all orders in the black hole mass. So it's only to fixed order in 1 over nu, but it's all orders in the black hole mass. So now we want to match the light cone bootstrap. So we need to specialize. We need to expand in mu. And what you find in d equals 4 for the first for the coefficient of mu in the anomalous dimension is this form. So this matches the bootstrap results. So it confirms this formula. And note also that if we take the mu to infinity limit, then we get this leading order term minus nu over 2k. So that was what we found in the anomalous dimension for a classical orbit. So the large nu limit indeed reproduces the classical orbit trajectories from the quasi-normal mode energies. Okay, well you can go to the next order in mu, and again it matches, and you can go to order mu cubed and get a new prediction. So it's not complicated to go to whatever order in mu you want. Okay, any questions about that calculation? Okay, so now let's go back to what I started with, and I want to show that these orbits are analogs of scars, perturbatively instead. So as I said before, these double twist operators are energy eigenstates at infinite CT and perturbatively in 1 over J. And now we want to work in this perturbative limit, and we want to check whether these energy eigenstates obey the ETH. So here I displayed it for your convenience. So we have the expectation value of some light operator in these heavy states, E and E prime. There's a diagonal term, which is a smooth function of energy. And then there's the off-diagonal terms, which are exponentially small in the entropy, times a smooth function of the energy, times some random matrix R. At least it's random in a certain range of energies. So that's the form of the ETH, and a quantum scar is something that violates the ETH. So in particular, we want to check if O light in the double twist states is a smooth function of energy. So how do we check this? Well, in a black hole microstate, the 1-point function is suppressed by 1 over lambda. So you can compute it. There's a paper by Maldacena and Grinberg who computed this 1-point function, and it's very small. In our case, we want to show that it's not 1 over lambda suppressed. It can be order 1. So that means that it's no longer a smooth function of energy, because it depends dramatically on what eigenstate, or on what approximate eigenstate that you choose. So to do this, let's give a simple toy model. So we assume a cubic matter coupling. So what that means is that the 3-point function is equal to G, this coupling. So we want to obtain the 1-point function of OL in these double twist states. And to do so, we can apply the Light-Kuhn bootstrap to this 5-point function written here. So we have two heavy operators and 3 light operators. And this was considered in this paper by Antunes et al. From this year. And we basically follow their paper almost exactly, just generalizing to operators with different dimensions to get the answer. So the way the Light-Kuhn bootstrap works is we first look at one channel and then look at another channel and try to reproduce the answers. So let's first take the limit x14 squared goes to 0. So that means that the 2 heavy operators approach each other. So in this limit, there's a singularity from O heavy, and that goes like 1 over x14 to the 2 delta heavy, and then we just have the 3-point function left over. So that's the easy channel. So now we have a cross channel, which is, so here, one of the heavy operators goes to one of the light operators, and also the other heavy operator goes to another light operator. So that's x1 goes to x2, x3 goes to x4, and you can compute that double OPE limit, and you find the following expression. Here, G is called the collinear blocks. It depends on K1 and K2, which label the 2 operators in the 2 OPE channels, and then another spin variable which parameterizes 3-point function of operators with non-zero spin. So it's pretty complicated. This PKL is a product of 3 3-point functions. So there's a heavy light K1 3-point function, heavy light K2, and then the thing that we want, which is the 3-point function of OL with the 2 intermediate channel states. So that's the thing that we want, namely the expectation value of OL in the double twist states. Okay. So now we examine the dependence of G on 2 of the cross ratios, and what you find is that the operators that appear in the intermediate channel have the appropriate twists for double twist heavy light operators. So that's the correct expectation. And then we just need to match the dependence on the other cross ratios. So we take the limit delta heavy goes to infinity, and here's the final expression. So the key point of the bootstrap is that on the right hand side we have something that is singular as U2 goes to 0. On the left hand side we have something that looks non-singular. So the singularity has to come from the sum over this spin parameter L. So you can solve the crossing equation. So you can check that this this entente is enough to solve the crossing equation. And so this was the product of the three-point functions. And finally, we get the desired expectation value of O light in the two double twist states. So that's the thing that we're interested in for ETH. So the details are not that important, but qualitatively, the important point is that it's of order G, and it's not suppressed by 1 over lambda or 1 over CT. And so therefore, it's much larger than the black hole answer. So that implies that the ETH does not hold in this family of approximate energy eigenstates. So, of course, this is not a true violation of ETH, because ETH does not have to hold in resonance states, and these operators are only eigenstates perturbatively in spin. So we can call them perturbative scars. So that's the name we can give them. And in fact, this is similar to one of the models that's considered in condensed matter called the PXP model. So this is actually the model that models the experiment that I discussed at the beginning with the chain of Rydberg atoms. So in that model, we also don't have true scars, and they're expected to eventually thermalize. So it's a similar situation. So let's examine some other similarities to scars. So in condensed matter physics, the scars generally have a subvolume law entanglement. In our case, we have a black hole, so the RT surface is always going to be repelled by the horizon, and we get a volume law entanglement entropy. But that's not a contradiction with the condensed matter models, because again, in the PXP model, the entanglement is thought to have a small volume law term, which is responsible for thermalization of these almost scars. And another interesting thing that we saw is that these orbits they come in a tower of approximately evenly spaced states, because the tower of orbits in pure ADS is approximately exactly evenly spaced, and the corrections to the ADS dimensions are small. So this tower it shows up a lot in the literature. For example, a certain kind of hover model has a tower of exact scars. So it's an interesting connection. So I just want to point out that there are other kinds of long-lived quasi-normal modes. For instance, for large black holes, if you look at the gravitational quasi-normal modes for odd parity, they take this form, and the decay time is proportional to the Schwarzschild radius, which is much bigger than the expected thermalization time, and so these are very long-lived. However, this is pretty different from our case, because there's no parameter like mu over j to some power in which this decay time is non-perturbative. So this is a different kind of situation.
These are just hydrodynamic modes.
Yeah, exactly.
So maybe one case that's more close to your situation is a holographic superfluid.
Okay.
So because I mean, the reason you're getting scars is that you basically have you have your very thermal kind of system, and you have a kind of weakly coupled sector that's also weakly coupled to the system. And so in a sense, it looks like a scar because they only talk to each other a little bit. I wonder if maybe a holographic superfluid is another example of this, where you have some black hole with a condensate, and it's strongly thermalizing and so on, but you still have maybe like weakly coupled superfluid phonons,
okay,
which one might also say kind of within perturbation theory maybe look like scars.
Yeah, that sounds great. I haven't studied those models, but I'll definitely look into that. That sounds great.
I have a question.
Yes.
Is there a way to interpret the ISCO or like orbits close to it in terms of the dual CFT?
Yeah, so that's where the Reggie trajectory ends. I don't know. I don't know a more interesting interpretation, but that, I mean, these are finite. The ISCO is the minimum spin for which these orbits are stable, and therefore the minimum spin for which we have these double twist operators.
But if you didn't know about ISCOs, would you be able to just say from the CFT that the trajectory has to end at some specific spin value, or?
I think if you knew it to all orders in mu, but that would require doing the bootstrap to all orders in mu, which maybe is kind of difficult. Yeah.
Thanks.
Sure. Okay, so let's conclude. I think I'm running out of time. Okay, so there's some interesting open questions, so let's go through them. So we could compute these things for more general black holes, like charged black holes, spinning black holes, etc. A more non-trivial thing is recently for asymptotically flat black holes, an exact Bohr-Sommerfeld condition has been derived, and it's very surprising because it involves quantum periods of a supersymmetric gauge theory, which you might never expect to happen, but it turns out that the wave equations are the same. So that was derived in this paper, and there's just an exact expression for these things. So it would be interesting if there was an ADS computation that's like that, because then we would be able to give an exact answer for these anomalous dimensions of heavy light double twists. That's pretty interesting. Another question is, these non-perturbative spin effects exist because of the black hole horizon. But what if we're not in a geometry with a horizon? Instead, we have a star or a fuzzball. Can we see this in the boundary theory? So that would be interesting. And finally, we eventually want to understand the connection to condensed matter physics, in which the PXP model is the most similar to our case. So there's some tantalizing possible connections involving the Bohr-Sommerfeld quantization and periodic orbits in that model as well. So it would be good to understand better the connection to our case. So let me stop there, and thank you very much for listening.
Questions for Matt?
Yeah, sorry, can I ask a question? How do I reconcile the fact that in ordinary numerical bootstrap, when it's pushed to high enough derivatives, people do find real dimensioned operators that sit on these trajectories of with matching the 1/L expansion with no complex contributions?
Do you mean heavy light?
Nima, I think he said there is an eigenstate. It's just the black hole. The true eigenstate is the black hole.
Yeah, but the black hole doesn't correspond to, like, that's delta heavy. That doesn't really correspond to a double twist operator. I thought that
it does. It's another black hole. It's another microstate.
I see. So I see. You're saying the reason you're getting imaginary contributions, at least in the bulk, is because obviously these are stable orbits. They decay by radiation.
But what they decay to is, what the actual state should be.
The actual state. I see.
Yeah. So in other words, do you think there are resonances, which means that there's sums over microstates over a small range of energies, which is a sum over black holes?
I see.
Yeah.
Okay. Thank you. Can I also ask about your decay rate calculation?
Yeah.
To get the decay rates, you computed. I mean, it looked like you computed just a wave equation with boundary conditions with ingoing particles into the horizon. And that's a general answer. That has nothing to do with orbits of anything. How did you relate it to particular orbits of like you have did you take the overlap of that state with the wave
Yeah.
function with the right quantum numbers and you say that's the decay rate?
Yeah, so the wave equation that we solved was the thing in the middle of the page here, and there's this source on the left-hand side. So this the source comes from the specific
I see. I see.
circular form of the orbit.
I see. Okay, I missed that.
Yeah, so I probably wasn't clear. So you could also do non-circular circular orbits, and then the source would have a different form.
I see. Okay, thank you.
Question?
Is there a sense like the the small fraction of the Hilbert space that's occupied by these scalar states and condensed matter? Do you have a quantitative way to say the fraction for these perturbative
Yeah.
stars?
Yeah, so the entropy of black holes is exponential. Sorry. The entropy of black holes is the area over 4G Newton. So there's exponentially many of them. Yeah, but there's only polynomially many of the double twists at fixed energies. So it's exponential versus polynomial.
How difficult is the generalization of the story to spinning radius black hole?
Yeah, you have to deal with stable orbits and curved spacetimes, which is not really that fun. I mean, they the equatorial ones are pretty easy, but then yeah, it's probably simple to do it when they're very far away. But if you want to know the full trajectory near the ISCO, it's going to be complicated. Yeah.
So you expect the large spin version of this would be okay, but
Yeah, it should be. Because in that case, yeah, in that case, the black hole has a small effect and it should be easy.
So in the spinning case, you have this extra conserved quantity called the Carter constant.
Yeah.
What is that? How is that related at all? Do you have a guess for how that's going to be related to anything on the CFT side?
It's a good question. Yeah, it's a really good question. I don't know. Yeah, I mean, indeed, this is a separable system in the bulk because the Carter constant exists, but I don't see a natural role for it on the boundary. So
I think people have shown that it's. I mean, like a long time ago, people showed it's related to the existence of a preferred like killing spinner. So I mean, that's just another word to help you.
yeah, I think it should be a killing tensor. But yeah, but
Sorry, yeah, but that, yeah, okay, yeah, but I think that tensor comes from the existence of some spinner.
okay, I see.
Yeah.
Yeah, it's an interesting question. I don't know. Yeah.
Okay, if there are no more questions, let's thank Matt again for his nice talk.
See you later.
Thanks, Matt. Really, really interesting. Thanks a lot.